In this video, we're going to learn about continuity theorems. The limit laws leads to an important result about in continuous functions. The theorem says that if fx and gx are continuous at c0, then fx plus or minus gx and fx gx are also continuous at the same point. In addition, the quotient is continuous at z0 if the denominator function is not zero at the point. So we are not going to prove this one. We will not prove this result in this discussion, and you can see that it's a straightforward application of the definition. Instead, we're going to look at a important application, especially when we want to find the limits. We can use this idea to find the limits because we know that if a function is continuous, the limit equal the function value. So we can use that idea. Before doing so, we're going to look at two special cases. First, we show that the constant function and the linear functions are continuous on entire Z everywhere. So let's look at one by one. For the first one, let Z0 is an arbitrary point and also pick an epsilon, positive epsilon. Now to see that the constant function is continuous, what we can do, we pick any delta. You can see why we can do that. Pick any delta, and when you do that, you can see and then consider the situation where z minus z0 is less than delta. And then it implies that if you look at the difference between the two functions, fc minus fc0, which is c minus c0, c minus c, which is equal to 0, that means automatically less than epsilon. That means it doesn't matter what c you pick, it's automatically less than epsilon. So that means it is continuous by the definition. And then also, thus the constant function is continuous on c. So we can see that. Now let's look at the next one. For fx equal z, what we do, we pick delta equal epsilon. It's a very interesting situation. Delta equal epsilon. Then if you pick any z, if you consider the situation where the absolute value z minus z0 less than epsilon, you can see as before, you consider the difference, then the difference simply becomes z minus z0 because a linear function, and see, so by the condition, this is automatically true because we pick delta equal epsilon. So that means that's exactly what we want to prove by the definition. So again, by the definition, the linear function is continuous. So those two cases like behave very interestingly, like a different. For the first one, you pick delta equal any delta, any positive delta. For the second one, we pick delta equal epsilon, and it works. So this established that fc equals z is a continuous function on the whole plane C. Now let's look at a few other cases. For example, the theorem actually implies several interesting situations that are very important for the future. For example, the polynomial function. So we can write a polynomial function in the form a0 plus a1z a2z squared up to an zn, like that. That's what we call a polynomial in C, where ai's are constants. So then you can see that it's also continuous on C because of the result, because these are product and sums, because the theorem says the product and sums are continuous. So because the constant function and the linear function is continuous, it gives you this one, because you can see any product you can write as a product of linear functions. For example, if you look at Z3, which is z times z times z, since we know that the z is continuous, c cube is continuous. So likewise, you can show that any term of this form is continuous, and we also show that the constant function is continuous. So this leads to the source that these polynomials are continuous. So in addition, the rational function in Z, which are quotients of two polynomials. So we have two polynomials, and then we can divide the two, and you can see that n need not to be the same. So in an m, so you can see that the rational function is also continuous when the denominator not equal to 0. And let's look at this important application. You know that one of the conditions for a function to be continuous is the limit equal the function value. So we can use this idea now to find limits of certain functions. So now instead of finding the limit, we can actually evaluate the function at the point if we know that the function is continuous. This is what we normally call the substitution rule. So you can use this as a shortcut to find limits. And also it only works when the given function is continuous. So that's what we need to check, whether this function is continuous. So let's look at few examples now. Let's look at this example. So we're going to use continuity theorem here. So the question is, find the limits as c goes to 2i of the functions a if c equals z3 plus 4 z plus 5, and b c plus 2i divided by z, and then hc, which is c squared plus 4 divided by z times c minus 2i. You may remember that we solved this problem earlier using the limit laws. Now as a shortcut we try to use the continuity theorem, and you can compare the difference. You can see you can get the answer much quickly now. So for the first one you can see that which is a polynomial, so it is continuous everywhere on C. In particular is also continuous at this particular point c minus 2i. So because of the continuity condition, you can see that the limit equal the function value. So therefore by substituting limit equal the function value, so you substitute the value to the function and then simplify and you get the value. So that's like a shortcut to find the limits. If you use the limit laws, you have to break it down to several parts and find them. So that's like a lengthy process. But right now you can get the answer much quicker using the continuity rule. So try to see the difference between the two. For the second one, you can see second one is a rational function, and also which is continuous at z equal to I, because the denominator not equal to 0 for this value. So because of that, instead of the limit, you can plug in the value and then simplify and you get the value 2 in this case as before. So you can get the values much quicker using the continuity theorem. So let's look at the third one. You can see the third one, which is not a continuous function at 2i, because we see the factor z minus 2i in the denominator. Because of that, it is not continuous. So that means you cannot use theorem 217 directly for this problem. But you notice something: when we want to find the limits, we know that we only look at values in the neighborhood of 2i but not equal to 2i. Because of that, under that condition, you can factor uh, the given function. So when you factor, you get this, and you can see that we are assuming the values which are not equal to 0 and not equal to 2i. Because of that, especially not equal to 2i in this case. So because of that, you can cancel these two factors because they are not 0. There are some values not equal to 0. So you can simplify it. So you end up getting this one. Now you can see that this new one or simplified one is actually continuous at 2i. Because of that, since we are considering only values which are not equal to 2i, you can see these two limits equal. Now for the second one, for the simplified function, actually we know that that's a continuous function. So you can use the continuity theorem or the substitution rule. So you can get the answer. Yes, they are equal to each other. And then simplify and get the value 2. So you can see this is like a shortcut that we can use using the continuity theorem, but you still need to make certain observations here. Okay. So now you can try these problems as practice problems. So see the difference and how you can use the continuity theorem instead of the limit laws to get the answer um, in a quick way. And if you cannot find the limit, say so why you cannot use the limit laws, why you can use the continuity theorem for these problems. And so we have several interesting problems here, and you can discuss some of them in the discussion board.